So we're moving on to confidence intervals and inference for means. So it's going to look really similar to what we did before. Just a couple things changed. So what I want to kind of do is just give some of the basics of what we're going to talk about. So now what we're doing, again, we're moving on to up a little bit better. Inference for means. So here's the deal. What we just did is we just did inference for proportions. So if you think about it, what we did is, and we took the test on is we did this as p hat plus or minus z star p hat 1 minus p hat over n. And that was our one sample confidence interval for proportions where we had a point estimate. So again, if you think about it, this was our point estimate. This was our critical value. And this was our standard error. So again, what we did for a proportion was we said, we're going to make a best guess of what the center is using our sample. We're going to count a certain number of standard deviations or standard errors in each direction. So it gave us a range of values. Well, here's what it looks like when we deal with means. For means, it's going to be X bar. It's still going to be plus or minus. Our critical value actually changes to this idea of something called T star. I'll explain what that is in a moment. And then this is our new standard error. And so just so you know, again, I pointed it out on the formula sheet for proportions, where I said, hey, here's what we're talking about with proportions, standard error for proportion, one sample. We had p hat, we had our standard error, X bar for means, and then there's our standard error. So the idea is still the same. We have a point estimate, a best guess. We're going to add and subtract a certain number of standard deviations. Now, here's the reason why it's a T instead of a Z. In the world of proportions, we're basing things on that Z, which is this normal distribution or this normal curve. This is kind of what our Z looks like. When we're dealing with means, because we don't know the standard deviation. So in this case, we don't know the standard deviation, so we're going to use our sample standard deviation. This is what it looks like. It actually kind of looks like this. So what it is it kind of looks like that normal distribution, but it's a little bit fatter in the tails. The main reason is that as we have smaller sample sizes, there's an okay chance that we could end up getting, two samples. Imagine we had 500 people taking a test, and I randomly took 2 people. I could randomly take 2 really low scores. I could take 2 really high scores, or I could take 1 of each, and that's where I'd be in the middle. So what we have is this is a T distribution, and a T distribution looks like a Z distribution as my sample size increases. So as I take a larger and larger and larger sample size, this T gradually, these 2 tails flatten out, and this bubble in the middle gets a little bigger. It ends up looking like Z. So the big formula that we're going to use here is this thing. It stands DF. It stands for degrees of freedom. And the degrees of freedom are going to be equal to my sample size minus 1. So what that means is when I'm working on a formula, once I know all but the last part of my sample, I can figure out that missing piece. So again, let's think about it this way. You took 3 tests. I told you took 3 tests, and you had an average of an 80. What are your 3 test scores? And the problem that you have is that it could be a lot of things. You could have had 3 80s, you could have a 70, an 80, and a 90, you could have a 60, 80, and 100. There's a lot of them. But now I'm going to say you had 3 tests, you had an average of an 80. You got a 75 on the first one, and you got an 80 on the second one. Well, now you could actually figure out that that third one was actually an 85. So that's what degrees of freedom are. Degrees of freedom basically say once I know all but the last piece of a sample, I can estimate, I can figure out what that last piece of the sample is. So I'm going to show us how to do this today with our example today. So we want to estimate the average weight of an Oreo cookie to determine if the average weight was less than advertised. I selected a random sample of 30 cookies and found the weight of each cookie in grams. The mean weight was 11.1921 grams with a standard deviation of 0.0817 grams. Make a 95% confidence interval to estimate the true mean weight. So again, point estimate. In this case, our best guess is X bar. So what we're going to say is, without knowing anything official, we're just going to go ahead and say that we believe that the point estimate at the center is our X bar of 11.1921 grams. Now, the next thing we want to look at is we want to look at it in terms of the population. The population here is going to be all Oreos. And the parameter here is going to be mu. And this is going to be the true mean weight of all Oreos. Our sample is going to be n equals 30, the Oreo selected. And in this case, the statistic we're going to use is X bar equals 11.1921. Was the sample a random sample? Well, it said right up here, random. So yes. And why is that important? It allows us to generalize our conclusions to all Oreos. And what it also allows us to do is it allows us to say that the thing is unbiased. And since it's unbiased, we're going to go ahead and use that X bar equals 11.1921 grams as our best guess of center. What is the formula for calculating the standard deviation of the sampling distribution? Okay, so this says sampling distribution. So in this case, going back to chapter 7, what we determined was that the sampling distribution, the standard deviation of the sampling distribution of means was equal to the real standard deviation divided by the square root. So that's way back. And again, if you want to remember, it's right here, sampling distribution. Now, here is the deal. We don't know the real standard. We don't know the real standard deviation, because if we actually knew the real standard deviation, there would have been no point to do this whole exercise, because to know this is to know this mean. Like, I need this answer to calculate this. Now, let's go ahead and see what we're going to do. So again, we're going to do the 10N check here. So we're going to do 10N, 10 times 30 is 300. We're going to compare that to big N, and we're going to say that it's safe to assume more than 300 Oreos. So now here's the deal. Because we did that, we are going to use, instead of this true standard deviation, we're going to use the standard error. And what we're going to do is we're actually going to do SX over the square root of N. So we're going to actually use our sample's standard deviation to estimate it. So in this case, that's going to be my 0.0817 divided by the square root of 30. And that's going to give me 0.0149 grams. So this one right here kind of does, if you think about it, this was our center check. This is our random check. This is our independent check. And now what we're going to do is we're going to do our large enough check. So this is what this is. This is the large enough check. And remember, with proportions, it was 10 successes and 10 failures. But when we're dealing with means, what we need to look at is we're going to look at one of now 3 different things. The first thing we're going to look at is, was the population described as normal? And in this case, if I look back up top, it says nothing about normal, so nope. The second check is our sample size. Our sample size is 30. That's greater than or equal to 30. By the central limit theorem, bingo, we've got our shape. And what we're going to actually look at today, or in this unit, is we're going to add another check. If our sample size is less than 30, what I want to do is I want to actually look at the sample distribution. So like actually what the sample looks like. And what I'm actually going to look like is I am going to look for several things, or not several, 2 things. No strong skew, no outliers. So this is going to be where we're going to kind of move towards. And what this allows us to do is, if we've done this, it allows us to figure out our T star. And what is going to happen with our T star is we are going to base that on our degrees of freedom. So our degrees of freedom equals n minus 1 equals 30 minus 1 equals 29. So what we're going to do is we're going to go back to table B. And here's how we work with table B now. Remember, when we dealt with table B before for proportions, all we really cared about was that infinity row, because that's what we dealt with proportions. Well, now what I want you to see is I want you to see how we are going to, let's better focus. That's somewhat better. We are now going to look at this column right here, 29. We're going to drag our pencil across till we get to the 95% column. 95% with a degrees of freedom of 29 tells me 2.045. So that's going to tell me that the T star here is equal to 2.045. So what we're going to actually do is we're going to find ourselves the margin of error for a confidence interval. We're going to use that T star. And basically what's going to happen is what I basically said here. The way we're going to figure it out, our degrees of freedom again are 30 minus 1. They're 29. So now from table B, we're going to find out that our T star is equal to 2.045. So now, figure out margin of error. Margin of error is our T star times our standard error. So in this case, it's going to be our 2.045 times our 0.0149, and that's going to give me 0.0305. Now, 95% confidence interval, what I want to do now is I'm going to take my X bar plus or minus my margin of error. So in this case, it's going to be 11.1921 plus minus 0.0305. If I add and subtract that, the range of values I'm going to get is 11.1616, 11.2226. Interpret the interval. We are 95% confident. The interval from 11.1616 grams to 11.2226 grams captures the true mean weight of all Oreos. So again, the formula we're going to use is what I just wrote up here. It's going to be X bar plus or minus T star times SX over the square root of M. And it says, according to Nabisco, an Oreo weighs 11.3 grams. Does our confidence interval provide convincing evidence that the true weight is less than 11.3 grams? And the answer to that is yes, because 11.3 grams is not included in our 95% confidence interval. All of the plausible values are less than 11.3 grams. So it's going to be very similar in many ways. So what I wanted you to see is just basically the concept stays the same. So when we do this, we're still going to do panic the same way. We're just going to change one of our checks in the assumptions, a large enough check. And what we're also going to do, the formula obviously changes because we're dealing now with means instead of proportions. But everything else in terms of the process is going to stay the same. The calculator commands are different, but at the end of the day, we're still kind of following the same logic path. So hopefully that helped. Next class, what we're going to do is we're actually going to do our first like full-blown panic on this one. This one was just kind of an introduction to the concepts.